Okay, so last class, we talked about applications to physics and engineering, section 6.6, and we learned about problems involving cables and work involving bringing a cable to the top of a building and the work needed to stretch a spring and so forth. And also we talked about the work needed to pump water out of a tank. So I want to do another tank problem with you. So I'm going to give you a moment to copy this example down. Okay, so hopefully you've had opportunity to copy the example down. All right, so in this problem, in our example here, we have a tank that has the shape of an inverted circular cone. Okay, so we're talking about a tank that looks like an inverted it's an upside down cone. And the height of this cone is 10 meters and the base radius is 4 meters. And we're filling the water to a height of 8 meters. What we want to do is we want to find the work required to empty the tank by pumping all of the water to the top of the tank. And in this case, we don't have we're not using pounds for force here in this problem. Okay, the problem that we did last Thursday, the problem we had, the weight was in pounds, but now we're going to find the weight another way. So density of water is 1,000 kilograms per meter cubed. That is actual fact. How many maybe knew that or heard of that in a physics class or a chemistry class? Okay, Justice has seen it before. Very good, very good. All right, so how are we going to do this problem? Well, we're going to do the problem, we're going to do the same approach that we used for the other tank problem we did. We're going to take our volume of water and break it up into layers. And the layers are a certain distance from the top of the tank, and we need to figure out the work needed to pump each individual layer of water to the top of the tank. And once we find that work, we're going to add up. Once we find those work values, we're going to add them all up as a Riemann sum, and then the Riemann sum will turn into an integral as we take more and more layers. So let's take a look here at the solution. So I start off, of course, with a picture. Okay, so here's my inverted tank here. And the tank is 10 meters high, and the base radius is 4 meters. Okay, so let me give you a moment to copy the tank down. Let me know if you have any questions. Now, I guess I can point out a few more things. So what I've done is I've drawn the water. Here's the water line. Right, here's the water line. And the water line, the top of the water is 8 meters. And then here is my ith layer of water. And of course, I have to find the volume of that ith layer of water. Well, I'm going to make the ith layer of water delta x high. Okay, delta x high. And the radius, so let me ask you, the ith layer of water in this tank, what shape would the volume have for the ith layer of water in the tank? I mean, what would the shape be of that layer of water? Well, it would be a disc. So you're a circle, but it has a height to it. So it would be a cylinder, a disc or a cylinder. It's not a washer in this case. There's no hole in it. It's a solid disc of water. Very good participation, everybody. So I have to find the volume of the ith layer of water. Okay, all right. Let me give you a moment here. All right. So now what we have to do, again, we have to find an expression for the volume of the ith layer of water. Okay, we have to find an expression for the volume of the ith layer of water. Well, so we know the volume of the ith layer of water is pi times r squared times height. So that a value, this a value here, the radius, we gotta find a value for a. We have to find an expression for the radius. Well, I know that a over xi, a divided by xi, equals 4 over 10. Now, how did I get this proportion? How did I get it? What property in geometry did I make use of to get that? That's right, Michael. Very good. Similar triangles. So I have, you know, a little triangle there, and then I have a big triangle here. So the radius A is to the height xi for the little triangle. That ratio equals the radius of the big triangle over the height of the big triangle. So A over xi would equal 4 over 10. And that means that A is equal to 4/10 xi, or A equals 2/5 times xi. Now what this means is we can express the volume, you know, V sub I is the volume of the ith layer of water. We can express the volume of the ith layer of water as a function of xi. So the volume of the ith layer of water, again, that's pi times r squared times height. Well, I have pi. My radius is a. Okay. In the picture, my radius is a. Well, no, the volume of that cylinder of water, the ith layer of water, is equal to pi r squared h, because it's a cylinder. So we got pi, the radius is a, and delta x is the height. And incidentally, my units are in meters. And so when I work this out, I substitute the a equals 2/5 xi in for a here. And so the volume is going to equal pi times the quantity 2/5 xi squared times delta x, and you'll get V sub I, the volume of the ith layer of water, equals 4/25 pi xi squared delta x cubic meters. So I like to put my units in when I do my work. So it just I know volume has to be in cubic meters in this problem. So this is a confirmation that I'm going about this the right way. How many like putting the units in the problem? How many find that kind of helpful? Okay, thank you, Kahindi. Very good, thank you. Okay, so now we have the volume, and ultimately what we need to do is compute the force of the ith layer of water. Now you'll notice that I have step 1, and then over here, this is step 2. Okay, this is step 2, right? Step 2. So because I'm dealing with meters, I'm dealing with meters and kilograms, I'm going to have to find my force using Newton's law. Force equals mass times the acceleration of gravity. Okay, That actually comes up in step 3. But before I can use that Newton's law in step 3, I need to figure out the mass of the ith layer of water. Well, density equals mass divided by volume. How many recall that formula, maybe even from middle school? Density equals mass divided by volume. Or how many have seen that formula before? And you must have seen it in a science class. Okay, Justice has, Michael has, sure. No, nothing new here. Density equals mass divided by volume. But that means then that mass is density times volume. Well, we're told that the density of water is 1,000 kilograms per cubic meter. Okay, that's the density. Okay. We know the volume of the ith layer of water, and so I'm just going to multiply density times volume. And incidentally, when I do that, what nice thing happens here? What nice thing happens to the cubic meters, to those units? That's right, they go away, they simplify out. Very good, Rodrigo, very good, Tina. So, you know, and again, that's telling me that I'm doing this problem the right way, you know. It's important to, it just kind of keeps me on the right track, let's put it that way. So then the mass for the ith layer of water, the m sub I, was going to equal 160 pi times xi squared kilograms. And now that I know that, I'm able to go to step 3 and figure out the force of the ith layer of water. Do I have, let me see here. Oh, that's a good question. That delta x should not go away, should it? Okay, let me fix that. Hold on. One moment. One moment. Hold on here. Yeah, the delta x needs to be there, class. So let me fix that. Please put this there should be a delta x. Delta x. All right, hold on. Let me try to write that in a little bit better. Let me maybe put it in blue. Delta x. Thank you. Thank you, Tina. Good catch. Good catch. So then, of course, there should be a delta x as well here. Okay. So the force of the ith layer of water, this is step 3. And this is done, this is actually example 4 in your textbook, but I'm just trying to work it out, show you a few extra details. So the force of the ith layer of water, that's the weight of the ith layer of water. I want to be a little careful. It is the force needed to overcome gravity to move the ith layer of water. That's force is mass times acceleration. Acceleration due to gravity is 9.8 meters per second squared. Okay. Let me just see here, one moment. Right. So the force is going to be then when you compute all of this, when you compute the 160 pi times xi squared times 9.8 times delta x, you should get 1568 pi x squared times delta x. So don't forget the delta x has to go there. Let me just hold on. That's right. 9.8 meters per second squared, Tyreek, is for gravity. That's right. Okay, so the force of the ith layer of water is equal to 1,565. The force of the ith layer of water equals 1,568 times pi times xi squared times delta x. Okay. And let me just see here. Let's check one thing here. One moment. One moment while you're copying that. Okay. So to make our lives easier, let's not worry about these units right here, okay? Because at this point, you know, I mean, basically once we got the mass of the ith layer of water, you know, once we got that, it's fairly straightforward. Okay, so once again, are there any questions up to this stage here? The force for the ith layer of water equals 1,568 times pi times xi squared. Sorry, that's a 2 there. Xi squared times delta x. Are there any questions? All right. Well, now what do we need to do? Now that we know the force for the ith layer of water in the tank to overcome gravity, what do we need to do next? The work. That's right, Michael. Now, once you have force, you can compute the work. Because we know that in this problem, that this ith layer of water here, it's a distance xi meters from the bottom, but then therefore it's 10 minus xi meters from the top. So work is force times distance. So, okay, and again, we don't need to worry about the units. Let me just see here. Hold on, I need my delta x, right? I need my delta x. And we know we're doing it right, so let's not hassle ourselves with the units. I just don't want you to worry about it right now, okay? So this is just like if I were in the classroom and I wrote something down, I might erase something, right? No big deal. So, okay, the force, the work needed to bring the ith layer of water to the top of the tank. Work is force times distance. We computed our force previously, and the distance is 10 minus xi meters. Now, actually, the delta x should really go here, right? That's where the delta x belongs, right there. So I like to put things where they belong. And so we're going to get then for the work 1560 times pi times xi squared times 10 minus xi times delta x. Okay. All right. Are there any questions so far up to here? Are there any questions at all? All right. Well, now what do? We found the work needed to bring the ith layer of water to the top of the tank. So what are we going to do with all these work values? Oh, you're right. It was 1568. Hold on. Yeah, hold on. Okay. Thank you, Tyreek. This is 1568 here. Let me fix it here. Hold on. Let me just double check. Yeah. Good. Thank you, Tyreek. Okay. Okay, no problem. So now the work needed to pump all the water out of the tank would be, we would take the tank and slice it up into all these ith layers of water and add up all the work. We would add up the work to all the work values. I want to say this the right way. We are adding up all these little work values. Each work value is the work needed to bring the ith layer of water to the top of the tank. But of course, if we break the tank up into smaller and smaller layers, the cylinders are going to fit better into that cone, and the approximation will be very good and for the total work. And of course, if we let in here go to infinity, if we let in go to infinity, then we're gonna get an integral. I have to fix the 1568. Hold on a moment. Okay, one moment. Okay, let me fix the 1568 here. All right, so oh, and the delta x, thank you. Good catch. We need the delta x here. Okay, let's talk about these limits. Tyreek has a good question. He actually was thinking what I was going to mention next. So what does these limits a and 0, what does x stand for? What does x represent? If you go back to the diagram, what does x represent in the diagram? Height, Colomb. Height of what, though? It's the height that, well, actually, you're fine. You're fine. The x represents the height. X represents the height that the ith layer of water is above. Well, x represents the height of the ith layer of water from the bottom of the tank. Well, this tank was filled up to 8 meters. It was filled with water to a height of 8 meters. So the bottom layer of water is 0 meters. That's the height of the bottom layer of water, and then the very top of the top of the top of the water is at 8 meters. So x goes from 0 to 8. Okay, Tyreek, are you comfortable with that? Excellent, excellent. Are there any other questions on that? All right, now I'm going to mention in the textbook, if you look at example 4, which is the example I'm working out here, they define their distance x differently. They define their distance x as the distance of the ith layer of water to the very top of the tank. And you might want to look and see how they're doing their problem. They'll get the same answer as I get. It's just their frame of reference is different. So I think it would be valuable to look at and see how this problem's done in the textbook. But I just kind of prefer my way. I like how I'm doing it. I'm measuring my x value is height measured from the bottom of the tank to the ith layer of water. Okay, let's move on. We need to integrate this. So this is just simple integration. Simple integration. Okay. We multiply the x squared by 10 and by x. And then it just becomes an integral. That's pretty easy to do. And in the end, you're going to get here, your answer will be in terms of joules. What you're going to get is 33, hold on. You're going to get 3,362,827.8, which is 3.4 times 10 to the 6th joules. Now, the reason I wrote it that way is, scientific notation it can be very helpful in helping us, state big numbers. And in WebAssign, you have to. So how would you type this in WebAssign? One moment. Let me give you a moment to copy that down. One moment. So in this problem, in your homework, they're not asking you to write it in scientific notation. But there is another problem in your homework. This is the one that's due Sunday, the second batch of 6.6 exercises. There's another problem where they want you to write the answer in terms of scientific notation. So the way, I'll just mention this because you know, in WebAssign, and WebAssign, the way you would write the scientific notation is 3.4 and then lowercase e and then a plus and then 0.6. Okay, that's how you would do that. I just want to, you know, there's a problem in WebAssign dealing with a satellite. You have to write your answer in scientific notation, and this is how, like, for example, you would enter scientific notation in WebAssign. All right, are there any questions on this particular problem? All right, well then we'll move on. So there are, let's see, Justice, how we got the 1568. All right, hold on. Let me go back here. So, you know, the 1560s are, you know, 1568s, as you know. But let me go back to where it originally came from. Yeah, so 160 times 9.8 is 1568. So this was step 3, where we were finding the force of the ith layer of water. So I hope that answer. I mean, let me see. Oh, okay. Are there any other good questions? Adriana, do you have a good question? Well, Mohammed, you'll get this in the recording. I'll make a recording of this, okay? And all right, let me go back to that last page then. Okay, are there any other good questions? All right, so this is the work. And, you know, it's important, right, to know how much work's involved because, like, for instance, a pump, you know, mechanical things break after a while, you know, depending on how much they're used, how much work's being done, and knowing the quantity of work's important because then you can, for instance, like the parts that are involved in making this pump, are they strong enough to handle this workload? You know, there are all kinds of things that go into finding work. And there are a lot of great applications in section 6.6. Another great application is hydrostatic force on a dam. And then there's another great application about moments and centers of mass. So I want to do moments and centers of mass. I'd like to discuss that. So what I'm going to do, I want to go into the ebook now. I want to go into the ebook. So let me go open the student view. So one moment here. How many have seen moments and centers of mass, maybe in an engineering class or physics class? How many have seen that? Might be a little new. All right. Well, let's talk about it here. So let me share the book here. Okay. So, you know, how many of you have tried to maybe balance a paper plate on top of their finger? I mean, everybody's maybe tried to balance a basketball on top of their finger, but to find the center of mass in that situation, you know, well, basketball is three-dimensional. I'm talking about like maybe a paper plate, try to balance it on their finger, or you know, something flat. You know, you see in Figure 8 here how that lamina, it's called a lamina, sheet there. Thank you, Justice. He knows what I'm talking about. There's a sheet, that blue sheet, which is of course not like a rectangular piece of paper or a circle. It could be any kind of funny shape, but it's essentially, we treat it like a two-dimensional sheet, and we're trying to balance it at a point P. Point P is your center of mass. It's the balance point of the plate. A plate is actually better to say than sheet, I think. I like the word plate better. And the plate is going to have uniform, what we call uniform density. In other words, the plate is constructed the same throughout. So what we want to do is we want to find the balance point or center of mass of that, you know, like what are the coordinates of point P? What's the center of mass? We call it the centroid. So first thing we have to recognize is that, you know, we're going to show you how we get the formulas, but we have a situation like in Figure 9 where you have two masses. Okay, you have a mass 1 and a mass 2, and there's a fulcrum in the middle, and mass 1 is a distance d1 away, mass from the fulcrum. Mass 2 is a distance d2 away. Okay, so how many have been on like a seesaw with a friend, a seesaw? And you know, how many recall doing that? I think pretty much everybody's been on a seesaw once or another time in their life. But how many kind of recall that? Okay, Mohammed has, Michael, Tina, quite a while ago, right? Now, you know, so let's pretend mass 1 and mass 2 are two people, one with mass 1, one with mass 2. Which person's going to be heavier? You know, maybe it's a father and his child, or a mother and her child. Which person's going to have more mass? The mass 1 person, M1, or M2? Who's going to be heavier? If that is balanced like the way it is, who's heavier, mass 1 or mass 2? Which is more? Which mass is greater, mass 1 or mass 2? Think about, you know, think about the seesaw. Yes, it's balanced. We're looking at Figure 9, and it's balanced. completely balanced. So definitely it has to be mass 1. If we're balanced, I mean, again, I think of, like, situation where, I think of the seesaw, but a person sitting the distance d1 away on the left, and another person sitting a distance d2 away on the right, and on a board, say, and the board is balanced at the fulcrum. The person who's heavier has to be the mass 1, person. And it's balanced because, like they show in the formula above, mass 1 times d1 in formula 6, mass 1 times d1 equals mass 2 times d2. So does this make sense, the formula 6 there? Are there any questions so far? Okay, all right, very good. Well, then let's continue on. So what we can do is, hold on here now. All right, so we suppose that the rod lies along the x-axis, like it shows in figure 9, with mass 1 at x1, mass 2 at x2. The center of mass is at x bar. Okay, that's right where the fulcrum is, at x bar. So the distance d1 would be the x bar minus x1. Okay, the fulcrum, the fulcrum. You think of an axis, the x-axis, going along that rod, that blue rod there, with mass 1 and mass 2 on it. If the fulcrum is at the coordinate x bar and mass 1 is at x1, then distance 1 is x bar minus x1. Similarly, mass 2 is at, on the x-axis, is at x2. Well, mass 2 would be a distance of x2 minus x bar. And so in formula 6, you can replace d1 and d2 with the x bar minus x1 and x2 minus x bar respectively. And then you distribute you can rewrite this equation as mass 1 x bar 1 plus mass 2 x bar equals m1 times x1 plus m2 times x2. And therefore, the center of mass, x bar, is equal to this weighted average of the masses in the numerator divided by the sum of the masses in the denominator. Okay, that's how you would find the center of mass. And this can be extended, by the way, to any number of masses. Okay, so x bar, if you had, like, say, multiple people sitting on this rod, multiple masses on the rod, the x bar can be generalized to any number of masses at any distances from, well, at any number of masses located at any coordinates x along the bar. Okay, and this is how you would find your mass. And these little individual mi times xi values are called your moments of the masses. Moments of the masses. Okay. And so if we go down a little bit here, the moment of the system about the origin, okay, would be equal to this m. Okay. So now, what we want to do is consider a system of masses now that are not just along a horizontal axis, but are in the xy plane. That's what they're showing in figure 11 here. Okay, so now we're talking about finding the center of mass for, in this case, they have 3 objects with 3 different masses located a certain distance away from the origin. Okay, and we want to find the center of mass. What would the balance point be? So the moment of the system about the x-axis would be equal to the sum of mi times yi. The sum of mi times yi. The moment of the system about the y-axis would be the sum, as they show in Figure 9, of mi times xi. So what you're trying to do is, if you're trying to find, again, think about a paper plate. You balance it on your finger, or some plate, you balance it on your finger. You have to balance out your x coordinates and your y coordinates for the plate to sit squarely on your finger and be balanced there. So the moment about the y-axis, which we denote as m sub y, would be equal to the sum of the masses times the distance xi that the objects are from the y-axis. See, the x sub I coordinate measures the distance that an object is from the y-axis. On the other hand, the moment of the system about the x-axis, m sub x, would be the sum of the quantities mi times yi, where yi is the distance, the mass m is from, the yi is the distance the mass sub I is from the x-axis, because yi is a vertical distance. That's your distance from the x-axis. Okay, so you can see that the picture here, that the x1, x2, x3 in Figure 11, that measures the distance that the objects are from the y-axis. Okay, which is why the moment about the y-axis is the sum where I equals 1, in this case 3, of mi times xi. Whereas the distance y is the y1, y2, y3 is the distances that the objects are from the x-axis. And so the moment of the system about the x-axis would be the sum where I goes from 1 to 3 of mi times yi. Okay, and so as in the one-dimensional case, coordinates for the center of mass would be given by the formulas in 11. X sub r would equal the moment about the x-axis, which is, moment about the y-axis, which is m sub y over m, and y sub r would equal the moment about the x-axis, m sub x over m, I should say. So the centroid is x bar, y bar. That's your center of your mass, or your balance point. Okay, so they have an example 6 here where they show you how to apply this. It's no problem, easy enough to do. But I'll just mention here, they have in example 6 masses 3, 4, and 8 at these points. So you're allowing for masses to be variable. Okay, you're allowing for masses to be variable, and and you have these different distances that the masses are. Now, what we want to do now, we want to go to a situation where we have a flat plate, and we could draw a plate in the XY plane with some region. What we're going to do is we're going to say that the plate has uniform density. So in other words, well, it's going to have uniform density. All right. So let me just see here. One moment. Yes. Okay. So that's what they're pointing out here. Uniform density. So we need to get a formula for this kind of situation, because right now we're able to compute the centroid if we have objects, located at points, different distances from the origin. But what if we were to consider all points? Okay, like a lot of points. Okay, like they show you here in Figure 13. Well, in this case, what we have to do is we have to consider, again, we're supposing that our region is the type shown in figure A, okay, and we want to find the center of mass. We want to find the center of mass. So what you have to do is again, I want to say this the right way. So the moment, I want to say this the right way, but I don't want to get too complicated, okay? But what they do is like, think about what the balance point is for this center of mass. Okay, it's going to be definitely above the x-axis, but it'll be some distance to the right of the y-axis. Okay, some distance to the right of the y-axis. Okay, so what they do is they break the region R up into a bunch of rectangles. And every rectangle, they have a dot in the center of the rectangle that's halfway between, halfway. So x sub I bar, and then you have an f of x sub I bar, which is the height of the rectangle. But I want to say this the right way, the center of the rectangle is x bar times 1/2 of f of x I bar. Okay, that's the center. Okay, and the centroid is at its center right there. And so what you're going to do, I want to say this the right way. You're going to be taking, I'm going to say this the right way. One moment. So density is equal to mass divided by volume. But in this case, we're going to treat density as mass divided by area. So mass is going to equal the density times the area. So if you're looking for the mass for this ith bar here, this ith bar in the picture, okay, assuming that we have, and we're assuming that our density is uniform, so we use this value rho here, to represent the density. The mass would just equal the density times the area, because density is mass over area. Mass is density times area. So density is rho, and then the area of the ith rectangle is base times height. The base is delta x, and the height is f of x I bar. So what you want to do then is the moment r sub I about the y-axis would be the product of its mass and its distance from CI to the y-axis. So I want to keep it very simple here. So one moment. Let me highlight this formula here. So the moment about the y-axis for this ith rectangle is going to be equal to the distance x sub I bar that the ith rectangle is from the y-axis times its mass. And that's how they're getting this moment about the y-axis for the ith rectangle in the picture. But what you're going to do is you're going to then, if you want to get the moment, okay, for the entire region about the y-axis, you got to add up all the little moments for each rectangle. And that's what they're showing in this highlighted formula here. The moment about the y-axis for the region is the limit as n goes to infinity of the sum I equals 1 to n of rho times x, rho times xi bar times f of xi bar times delta x. But then that'll just become the integral rho times the integral from a to b of x times f of x dx. That's what it'll be. And in similar fashion, you can find the moment about the y-axis. Okay, I'm sorry, in similar fashion, you can find the moment about the x-axis, okay, for the region. But first you have to find an expression for the moment about the x-axis for the ith rectangle. Again, these rectangles are coming from the picture here in figure 13. So in this case, what you're interested in is the vertical distance. And the vertical distance, since the rectangle is a height of f of xi bar, 1/2 of that height is where the centroid is, where the center is of the rectangle. So the height of that center is 1/2 f of xi bar. And that's how they get that. So the distance is 1/2 f of xi bar, and then you multiply it, hold on here, you multiply it by, hold on here, you multiply it by, the mass, which is rho times f of xi bar delta x. Hold on, let me get down here. Right, that's right. And so you'll get then rho times, for the moment about the x-axis for the ith rectangle, you'll get rho times 1/2 f of xi bar squared delta x. And then you'll get yet another formula for the moment about the x-axis for the region. Okay, because what you do is you add up all these individual moments. So the moment of the region about the x-axis would be when you take the Riemann sum and take the limit as n goes to infinity. You know, you break the region up into tinier and tinier rectangles. You'll get an integral rho times the integral of a to b of 1/2 times f of x squared dx. Okay, and so that's how you get this. That's how you get this. That's how you get the moments about the axes, which you're going to need because you have a region that's in the xy plane. You need to get the moments about the axes for the region. Absolutely lovely, beautiful. But remember, mass, since density is mass over area, mass equals density times area. Okay, and the area for your figure, for your region R, is going to be the integral from a to b of f of x dx. And so if you want to find the centroids, what you do is you just take, hold on here, I like to highlight that, one moment. I don't know if it'll let me highlight it, but one moment, let me try it again. Yeah, all you do is you take the moments for the x bar coordinate for your centroid, you take the moment about the y-axis and divide it by the mass. And what's going to happen is the densities will simplify out and you're going to get the ratio of these two integrals. Similarly, the moment of the region, no, the y coordinate for the centroid, y bar, is the moment about the x-axis divided by the mass. And again, the densities will simplify out, and then you get a formula, which is for y bar, which is the ratio of the those integrals. And so now you have a formula to compute the centroid. You have a formula to compute the centroid. Okay, and so I just thought it was good to give you a little guided tour of that before we move on to our example. We obviously want to apply the problem to a situation, right? To an example. Now I'll mention we assumed here we assumed that we had that the mass was or the density was constant. But when you take calculus 3, and you learn about double integrals, you'll be able to deal with situations where the density is not constant in the plate. The plate could have the density function. The density could differ from at different points. So that you have to wait for calculus 3. Who's looking forward to that? Who's looking forward to that? Uh-oh, I'm not seeing any hands up here. No, nobody. I mean, that's sort of the next natural thing. Okay, Mohammed, not really, but at any rate, I've given you a little idea of what's coming up. It's kind of like the James Bond movie. We're not going to see it till the spring, right? The new James Bond movie. So calculus 3 you won't take till the spring, but you have a little idea of what's coming up. So okay, that being said, let's look at an example here. Let me go back to our thing here. Okay, so here is another example for center of mass. And let me give you a moment to copy this example down and draw the picture, okay? All right. Okay, so we want to calculate, in this problem, we want to calculate the moments. We want to calculate the moment about the x-axis and the moment about the y-axis and the center of mass for a lamina with density 2 and the shape below. Okay, so, well, all right. What does this lamina seem to be a part of? What does this lamina seem to be a part of? I mean, we need a, I guess what I need is, I guess what I'm saying is, I'm going to need a function. I'm going to need a function, right? So all they've given me a picture of this plate. They've given me a picture of it, but I need a function to describe. You know, I need to know the function here. What would that be? Where's this? What's that function look like it's coming from? What shape? Okay, so what is it? Is it a rectangle? No, it's not a rectangle. That looks like a circle. That's right, Tina. And as a matter of fact, it's a quarter of a circle. What's the radius of the circle? Radius 2. So here's how I would go about finding the function. Hold on here. I know my pages are a little bit out of order. It happens. All right. So the lamina, okay, is 1/4 of the circle. 1/4 of the circle. The circle being x squared plus y squared equals 4 because the radius is 2, right? So that means y squared would equal 4 minus x squared. But then, how do we solve for y? This would imply that y equals plus or minus the square root of 4 minus x squared. However, for our function is above the x-axis, right? The function's above the x-axis. So the function it's never negative. So we have to say then that it would only be the plus part. Because why is that? Because y is greater than 0. If the function, I'll just redraw that quarter circle. It's above the x-axis, right? It's above the x-axis. So that means that the function f of x is always positive. Y is always positive. So therefore, y is going to equal plus times the square root of 4 minus x squared. Okay. And now that you have your function, now that you know what your function is, and x, of course, goes from 0 to 2, right? So now that we know that, we can work out the formulas. So first of all, the moment about the x-axis. The moment about the x-axis. Okay, one moment. Okay, I'm just getting this. One moment here. Okay, my pages are back in order here. So where am I getting this from? One moment, not now, one moment. I'll answer you always have good questions. Let me just first identify what this is. So the 2 is the density. They told us the density row was 2. The limits, of course, are from 0 to 2 because those are our x values. And then for the moment about the x-axis, in the integrand, we have 1/2 times the function squared. Well, this is my function. And so this is what we have to integrate. Yes, not now. Question? Question?
Yes, Professor. So I had a question.
Sure, sure.
So for mx, so we use mx because it's above x axis, and we use would we use my if it was like if it was just like on the y axis? I think I'm
Yeah, it doesn't matter where the region is. It could be anywhere in the XY plane. These formulas work in general.
So it doesn't matter if you just say x or y. It doesn't. Really
Well, no. What I am using, I am using a specific formula for the moment about the x-axis. The moment about the y-axis is going to be a little bit different formula.
Okay.
But you have to identify your density. Okay. And actually, you don't have to really know the density because when you compute the centroid, the density values simplify out. But it's okay,
Yeah,
All
I
right.
guess I just didn't write the complete. Okay. I was taking notes, but just it looked more like the y, I think, with like without the 1/2, or maybe I didn't write the whole. I'm not sure, but okay.
So hold on here. Go back here. So this is our function right here, right? And f of x, we determined. Now in the homework, usually they'll give you the function, and you'll have to draw it on your calculator. But in this case, they just give you a picture, and it's obvious that this is going to be part of a circle, and the function is going to be it's a part of a circle with radius 2. The function is going to be f of x equals the square root of 4 minus x squared, and we're restricting x to be between 0 and 2.
Okay.
So that's how we got the function, and now we're just applying it into the formula. Okay. So the moment about if you look in your ebook, there's a formula for this. The moment about the x-axis equals the density times the integral from a to b. A is 0, b is 2, times 1/2 times the function squared dx. And so you work it out, and you're going to get 16/3. You're going to get 16/3. That's your moment about the x-axis. Yes, Tyreek.
I wasn't sure where the 1/2 came from.
It's the 1/2 is part of the formula. It's part of the formula.
Oh, okay.
So hold on. Let me 1 moment. 1 moment. Let me bring back the ebook here. Wait. So you see here, you see the ebook here, right? So here's the moment about the x-axis. You see here the m sub x equals rho times the integral from a to b of a half times f of x squared delta x. I'm putting it in pink. You see the pink formula there at the end?
Yeah.
That's where I got it from. Okay, you see, does that help you a little bit? All you're looking at is the very end here. The beginning, m sub x, the moment about the x-axis, and then at the end equals that formula. That's where I got the formula. And incidentally, the moment about the y-axis, which we're going to do next, that's going to be this formula. That the moment about the y-axis is rho times the integral from a to b of x times f of x dx. So we went through the derivation, but of course it's going to take you time. I pointed out the highlights of the derivation of these formulas. But you'll need to look at the book if you want to really, what I mean is I think in the recording, I pointed out how these formulas were derived, but you might need to listen to the recording again, or go to the ebook just to look a little bit too. But the point is, we have formulas to compute these moments about the axes, and that's where they are. They're in your ebook. They come right after example 6. Okay, so now let me go back to the problem here. We continue it here. Okay, so we got 16/3 for the moment about the x-axis. We got 16/3. And now what we do is we want to find the moment about the y-axis. So the moment about the y-axis is going to equal the density times the integral from 0 to 2 of x times f of x dx. Again, that's that second formula. And here you're going to have to use the substitution. Okay, and when you do that, the moment about the y-axis will equal 2 times the integral from 0 to 4 times the square root of u times negative 1/2 du. Tyreek, are you feeling a little better about, at least you saw in the book where the formulas come from, right?
Yeah.
Okay, all right, good, good, good. Okay, so and again, the x is just that's part of the formula. The x, that's part of the formula there. And so all right, we just work it out. Now, when you have the negative of an integral, notice my limits go from bigger to smaller. If I absorb the negative in the integral, that switches the limits. So it turns out, when you compute it, the moment about the y-axis, is going to equal also 16/3. All right, are there any questions so far? All right, well then let me go back to the book again. Let me go back to the book here. Okay, now the here formula 12, which I put in pink, gives you the formula for the centroid, the center of mass, x bar, y bar. Okay, so now we're gonna find the center of mass. So we found the moments about the x-axis and the y-axis for this quarter of a circle region. Okay, we found the moments, but we haven't found the center of mass yet. So x bar is equal to 1 over a. A is the area of your region times the integral of x times f of x dx. And y bar of the centroid is 1 over a times the integral from a to b of 1/2 f of x squared dx. Okay, so those are your formulas for your centroid. Okay, so what we got to do is we have to apply the formulas. So back we go here. One moment here, let me. Okay, so the area of the lamina, okay, remember the lamina was a quarter of a circle. Well, area of a circle, for a circle, what's the area for a circle? Oh, you better know that formula. What's the area of a circle? Pi r squared. That's right, Tina. Okay, very good. So the area of a circle is pi r squared. And actually, in this case, since we have 1/4 of a circle, we're just going to take 1/4 and multiply it by pi r squared, and that's going to get us the area of our lamina. And so now we just apply the formulas. So in this case, the area, I didn't have to use calculus. I didn't have to compute an integral to get the area, but I do have to use calculus to get the centroid. So x bar is equal to 1 over a times the integral of x times f of x dx. And that's going to equal, well, we already, the integral, so we need to compute the integral from 0 to 2 of x times the square root of 4 minus x squared dx, right? We need to compute that integral. But we already did compute that integral previously when we found the moment about the, hold on here, about the y-axis. We got 16/3, but it was 16, but since we don't have the 2 in front of the integral, we have to take 16/3 and divide it by 2. So again, this integral, we computed 2 times that integral previously to compute the moment about the y-axis. So we're just going to divide, to get the value of this integral here, we're just going to divide that by 2. So we take the 16/3, okay, divide by 2. Because 16/3 was equal to 2 times this integral. And we don't have a 2 there anymore. So we take 16/3 divided by 2, and we get 8 pi over 3. Okay. I think, let me see here, I may have, I think I have an error here. I do have an error. This is an 8 pi over 3. This is 8 pi over 6. So there's an error here. This shouldn't be a 3. This is a 6 here. So please make that correction, class. Here, I'll just one moment. This will equal that happens sometimes when you skip a step. Hold on, I don't. One moment. Let me just work it out on paper here. Hold on. One moment. One moment. Maybe I'm second guessing myself. See, when you skip a step, it's usually. All right, so let me just write this as no, I'm right. I'm right. I'm right. I was right. This is equal to 8 pi over 3. 8 times pi over 3. Let me just see one thing here. One moment. Oh, I see what I did wrong. No, I did have an error. It's, I see what I did wrong here. Okay, this computation is okay. This is okay. But it's going to be 8 divided by 3 pi. Okay, it's going to be 8. My God, my goodness, hold on. No. Yes, that's right. I'm second guessing myself. 16 becomes an 8. 2 becomes a 1. You get 8 over 3 pi. Okay, that's going to be your x bar. See, sometimes when you skip a step, how many notice that maybe on the exam? Maybe they skip a step, leave a step out, or in their homework, but you leave a step out, and you end up making kind of a silly error. How many have had that experience? I'm sure. Okay. So I just demonstrated to you, how that can happen. Okay, so let me just write it out. It's 8 over 3 pi. Okay, are there any questions? Now, there were a few chats here. Okay, Colombe knows what I'm talking about. Michael, too. Thank you, everybody. Yep. And for y bar, we're the second coordinate of the centroid. You got 1 over the area times the integral of 1/2 times f of x squared. And here too, I have an error at the end. This also is going to equal, it's going to equal 8 pi over 3. Now WebAssign is going to want exact, 8 over 3 pi, sorry. That's your y bar. Not now, open up your ebook. Oh, I don't want to go quite yet to that formula. I will, but let me finish this. Your ebook, look in your ebook, section 6.6. Okay, the formulas come after example 6. Okay, you'll find them there. You'll find them there. All we're doing is we're applying the formulas. We're just applying the formulas. But I'll have a chance to, you know, help you a little bit. But let me finish this up. So that's your centroid. Now, incidentally, let me mention this. So x bar, y bar is going to equal 8 over 3 pi, comma, 8 over 3 pi. Now let's write that as a decimal. Now, incidentally, WebAssign is not going to accept a decimal for this answer. And this actually brings an issue up that few of you have emailed me about regarding the exam. So when you can get an exact answer on a problem, WebAssign wants the exact answer. It does not want a decimal answer. It doesn't even want a nice decimal answer. It wants the exact answer. And if you don't put the exact answer in, it's wrong. Okay, WebAssign, and because you know that's the expectation, the exact answers are the best, right? I mean, what I mean is, I'm not saying you didn't do the problem right, but train yourself to when you integrate something, put in the exact answer. WebAssign doesn't want a decimal answer, and it'll count it as wrong, and then you have to redo the problem in the first remediation. So just, you know, don't put in a decimal answer, right? Put in the exact answer. There's a big difference between okay, Notnell, I don't know why the ebook would not be available. I locked the homework up, but not the ebook. We'll deal with that in a moment. So all I'm saying is, I mean, this should be nothing new, right? You know that we always want exact answers when we can get them, and WebAssign wants that too. Okay, so all right. So let me just see here now. What's 8 divided by 3 times pi? We're almost done here. What's 8 divided by 3 times pi? What's that approximately equal to? Who can tell me? So on your calculator, take 8 and divide it by 3 pi. Tina, I get something less than. I'm glad I did this. I always like it when. Okay, Michael, that's more what I'm getting. Okay, so I'll round this to 0.85. And 0.85. So approximately, now here's where a decimal is helpful. I'm going to go back to the picture. So the centroid is 0.85, 0.85. I go back to the picture here. Okay, 0.85, 0.85 is roughly, well, it's going to fall inside this rectangle here, right about here. This is where the X bar and the Y bar is. Does that look to be, 0.85, 0.85? That's right here where the dot is roughly. If you were to try to take a plate that looked like that quarter circle and balance it on your finger, wouldn't your finger have to be where that blue dot is at the centroid, 0.85, 0.85? I mean, wouldn't that be where you have to kind of balance it? I mean, would one do? Let me put a little red dot. Just stay a few moments. This is would 1, would that be where the center of mass is at 1, 1, where the red dot is? No, you can tell by the shape. It's heavier inside. You have to go in a little bit. You have to go to where X bar Y bar is at 0.85, 0.85. That's the center of mass. How many think that's absolutely fascinating? How many think that's really, really cool? I mean, isn't that amazing? You found the center, you found the balance point for that region. I mean, yeah, I agree, Adriana. It's interesting. Michael's mind blown by it. Great. All right, well, that is section 6.6. I'm going to stop the recording.